Welcome back everyone. In this lecture, we will pre-process the data for the cardiac detection task. The pre-processing pipeline is very similar to the previous one, with the difference that we now have to somehow include the coordinates of the bounding boxes. We will again convert all images to NPY files for efficient storage and faster data loading. To tackle this problem, we use the following libraries: Pathlib for easy path handling, PyDICOM to read the DICOM files, NumPy to store the pre-processed files, OpenCV to resize all images, Pandas to read the provided labels, Matplotlib for visualization, and additionally patches from Matplotlib to draw the bounding boxes around the heart. As usual, I have already prepared the imports. At first, we read the CSV file containing the labels and store it in a variable called labels. We simply use pandas.read_CSV and pass the path to the labels file. You can find the CSV file called RSNA_hard_detection in the corresponding directory of this lecture. Let us have a look at some entries. You can see that our labels file contains the coordinates x0 and y0, which correspond to the top left corner of the bounding box. Next to that, it contains the width and height of the bounding box. This defines the location of the heart in a unique manner. Additionally, it of course contains the name of the DICOM file. You can directly see that we will later have to add the file extension again. Furthermore, it also contains the shape of all images. However, as all X-rays were of shape 224 squared when labeling them, we can ignore those two columns. Now it's time to define the route and the safe path and visualize some images with corresponding bounding boxes after that. As we want to reuse the original images provided by the RSNA Pneumonia Detection Challenge, we can use the same path as we did in the last pre-processing lecture. State2_train images. Please make sure to adjust this path to your corresponding directory. Regarding the save path, let's define that we want to store the pre-processed images in the directory called processed -hard -detection. Alright, it's visualization time. Let's use a 2x2 plt.subplots object to inspect 4 images. As usual, we define our loop counter variable and set it to 0 before creating the double nested for loop. At first, we have to extract the cth row of our labels data frame. To do so, we can use labels.ilog and use our loop counter as index. Next, we have to grab the patient ID by using the name column of our labels data frame to finally create the path to the DICOM file by concatenating our root path with the patient ID converted to a string. Last but not least, we have to add the file extension by using the with_suffix function and simply adding .dcm. We are now able to use PyDICOM.readFile and pass the DICOM path. We can extract the corresponding pixel array and subsequently resize it to 224 squared by using cv2.resize. To construct the bounding box, we need to access the coordinates plus width and height columns of our labels data frame. To do so, let's create 4 variables. At first x, which takes the value of x0, y, which takes the value of y0, width, which takes of course the value of w, and last but not least the height, which takes the value of h. Using those two coordinates plus width and height, we can now draw the rectangle around the heart. At first, we visualize the X-ray image by calling ImShow, to which we pass the DICOM array and CMap equals to bone. Next, we define the rectangle containing the bounding box by calling patches.rectangle, to which we pass at first the coordinates of the top left corner, in our case the tuple x and y, second the width of the bounding box, and third the height. Additionally, let's pass a parameter called line width equals to 1 to get a more narrow border, edge color equals to R, which draws a red bounding box, and last but not least, face color equals to none to make sure that our bounding box is not filled. We only want to draw the borders and not a solid rectangle. We now simply access our current axis object again and call @_patch, to which we pass our predefined rectangle. Now we simply need to update our loop counter variable and we're ready to inspect our images. Oh, and of course, we also should spell line width correctly. Perfect, everything worked, and now we can see 4 different X-ray images with their corresponding bounding boxes around the hearts. Alright, now it is time to write the pre-processing loop. As already mentioned, we use a similar routine to the one used for the classification task. However, to be able to distinguish between train and validation subjects in our dataset, we store them in 2 lists, which we save after the pre-processing is done. At first, we define our sums and sums_squared variables to compute mean and standard deviation later. Of course, we initialize them both to 0. Next, we create 2 lists called train_IDs and val_IDs to store our train and validation subjects. Now we can define the pre-processing loop. We code it in the same way as we did in the classification lecture, but without TQDM, because to be honest, you don't really need a progress bar when only working with 500 files. So let's write for counter, patient_ID in enumerate of list of labels.name. We loop over all patient IDs in our labels file. The first steps we have to perform are to create the path to the DICOM file and add the DICOM suffix. Moreover, we should read the file with PyDICOM, extract the pixel array and resize it to 224 squared. We can directly copy those steps from our visualization routine above. Let's directly standardize the current image into the 0-1 range by dividing it by 255. Additionally, let's convert the resized X-ray image to float 16. To decide whether the current patient ID is a train or validation subject, we can use the ternary statement again, which assigns the variable train or, well, the string train if our counter is smaller than 400, else it assigns val. We can now use a simple if-else statement which appends the current patient ID to the train IDs list if our train or val string contains train, else we append it to the validation IDs list. Based on this train or validation string, we can create the current save path by concatenating our root save path with the train or validation string. We can use the makeDir function to make sure that this path is created if it doesn't exist. To do so, we again pass parents equals to true and also exist underscore OK equals to true. As a reminder, passing parents equals to true simply creates all paths from the current path to the current safe path, whereas exist OK equals to true prevents the mkdir function from throwing an error if the path already exists. Let's now use numpy.save on the concatenation between our current safe path and the patient ID to store the current DICOM array in a corresponding train or validation directory. Last but not least, we only have to compute our image normalizer and update sums and sum squared if the current patient is a train subject. To compute the normalizer, we simply multiply 224 by 224. Next, we check if our train or validation string equals to train to finally update at first sums by computing the sum of the current DICOM array with subsequent division by the normalizer. Sums squared is updated by at first squaring our DICOM array with subsequent sum computation. Of course, we also divide it by the normalizer. Cool! Our pre-processing loop is complete. It should only take a few seconds to store all pre-processed images. To enable our dataset later to distinguish between train and validation subjects, we simply store those two lists. At first, we can save our train IDs in the processed hard detection directory as a file called train_subjects. We simply repeat this procedure for the validation subjects by replacing train by val. Last but not least, we only have to compute mean and standard deviation. As already shown in the last pre-processing lecture, we can get the mean by dividing our sums variable by the number of train subjects. In our case, we can simply divide it by the length of our train IDs. To calculate the standard deviation, we compute the square root of sums squared divided by also the number of train subjects and subtract the squared mean afterwards. Now let's print the mean and standard deviation so we can use them later in our dataset. Alright. We successfully pre-processed our data and computed mean and standard deviation. Perfect! In the next lecture, we will create the dataset. Thanks!